a road for you. We don't have the knowledge to maintain that infrastructure. And now, they're just gaining citizenship because they're here for a long time. If you live here for 15 years building a road, of course you can get citizenship. And now there's a land crisis in Africa. Where will Africans live? I am sorry for my continent.
Fractioning column, and we said that the various fractions are boiled off in such a way that those with the lowest boiling point come off at the top and those with the highest boiling point come off down on the bottom. Did we get to the alkanes? Okay, we were over here. Okay, just very shortly. Okay, we had a look at the naming of the alkanes. Okay, now, keeping that in mind that we had a look at the naming of these compounds, I just want to start from one end. People, the alkanes, we say they form what is known as a homologous series or a homologous group. That is just simply a group of compounds that have got similar properties. We say they have the same general formula and same general properties. We said the general formula for the alkanes was CnH2n plus 2, where n is any whole number. So if I have 5 carbons, I will have 2 times 5 plus 2, 12 hydrogens. Are you with me? Yes? Diesel is also an alkane. Yes, yes. They are mixtures of carbons. Petrol is between, I think, 5 and 10 carbons, and diesel is slightly longer. Yeah, but they all burn. Yes, because, yeah, but if you look at the general tendency of properties, petrol is a smaller molecule. Diesel is a bigger molecule. So the bigger the molecule, the higher the boiling point. So diesel, well, is a liquid that doesn't really want to evaporate. But petrol does, because it has a lower boiling point. You understand? It's got to do with the molecular structure, but they behave similarly under similar conditions. They can all be burned to get carbon dioxide and water vapor. All right. Okay, so we said they were saturated. What did that mean? Yes, that between the carbon atoms, there are single bonds, and each carbon is bonded then onto the maximum number of hydrogens. Just general boiling points increase with increasing molecular mass. We saw that in the fractionating column as well. The smaller molecules, the gases, came off at the top, and down at the bottom we got the lubricating oils and the fuel oils, which were larger molecules with higher melting and boiling points. We had a look at did we have a look at the combustion of the alkanes? No. Okay, because that is the next thing we must have a look at. Now, we've already said the alkanes can act as fuels, which means we can burn them and they produce energy, carbon dioxide, and water vapor. When we have enough oxygen, we get complete combustion. If there is too little oxygen, we get incomplete combustion. All right? Now, when we're going to have a look at the combustion of the alkanes, okay, yeah. The first one is methane. Methane looks like this. Yeah, we did that now. Okay. The second one is ethane. All right. Leave propane for a moment. Combustion of methane. When methane burns, what do we get? Carbon dioxide and water vapor. CO2 and H2O. Is that right? Okay. Same with this one. If this one burns, what do we get? CO2 plus H2O. Quickly take a pencil and a piece of scrap paper and try and balance them. Just quickly. The first one should be easy. But the second one, some of you might run into problems. Have you got it? No. Okay, let's quickly have a look at them. Let's do the first one, because the first one's easy. You shouldn't have problems with the first one. 1 carbon, 1 carbon. 2 oxygens, 1, 2, 3, 4 hydrogens, 2 hydrogens, we need a 2 there, but now, how many oxygens? 2 plus is 4, so we need 2 over there. Are you all with me on that? That's not a problem. Okay, but this one, how many carbons? 2. So, we put a 2 in there. How many oxygens? 2, 2, 4, plus 1 is 5. Let's have a look at the hydrogens. 1, 2, 3, 4, 5, 6 hydrogens. How do I get 6 hydrogens? I will need 3 there, but does this solve the problem with the oxygens? We have 4 and we have 3, that gives me 7. How do I get 7 oxygens? Well, technically, I would need 3.5. Okay, can I have a half? No. So what you're going to do is you're going to multiply everything with 2. Because when you have an equation, what you do to the left, you must do to the right, and you don't change it. No. So over here we will have 2. Over here we will have 7. There we will have 4. And here we will have 6. Okay. People, it just works like this. When we balance the combustion reaction of an uneven number of carbons, it's easy. It works out easy. But if you have an even number of carbons, then it's difficult to balance. So if I want to be nice, I'll give you the easy one. I'll give you an example with an uneven number of carbons. And if I want to test and see, can you really do balancing, I'll give you a number with even numbers of carbons. Yeah, it doesn't mean I don't like you. Have a look at propane. Propane is C3H8. Butane is C4H10. Okay, so quickly do the balancing. That one should be easy. Look at this one. The uneven number. 3 carbons. 8 hydrogens. So we've got how much? 6 plus 4 is 10. Gives us 5. That shouldn't be a problem. No. But this one, 4 carbons. So we go with the 4 carbons. 10 hydrogens. So we go with the 10 hydrogens. But now if we look at the oxygens, we have 8 plus 5 is 13. So how do I get 13? I will need 6.5. But I can't have a half, so I will need 2 there. I will need 13 there. I will have 8 there and 10 there. You multiply with 2, just everything. Okay. All right. So, over here, isopropane is a structural isomer. We've had a look at that. People, what does isopropane look like? Methane, ethane, propane with a branch on it and filled up with hydrogens. Okay, isopropane. I don't need to say more about that. We did that in the last period. All right. Now, in this next section, we've already had a look at the combustion of alkanes. We know they are used as fuels. When they burn, they give us carbon dioxide, water, and energy. During incomplete combustion, it is important to know that we get carbon and carbon monoxide together with the water and the energy. Some of the other reactions of the alkanes is something called substitution. Now, if I have a hockey team and I want to substitute a player, what must I do? I must take one out and I must put another one in. So in terms of substitution reactions with alkanes, we have to take something out and put something else in. For example, let's say I have got ethane plus, let's take bromine. Actually, let me write the bromine like this. I want to do it in a different color as well. Let's go and do that. And then I want to go there. And I want to go there. Okay. We must take something away because all the bonding places have been filled. The easiest would be to take a hydrogen out, okay, and add a bromine, and that forms HBr plus my halo alkane. Can you see that? We've taken something away and we've put something else into its place. Substitution. Now, the alkanes are not very reactive. Sometimes we need to encourage the substitution reaction. It sometimes goes a little bit slowly, but we can make it happen. What would the name of this compound now be called? Well, we no longer have ethane because we've got a bromine stuck onto it. This thing would be called bromoethane. Okay. Now, I can repeat this process. Okay, and I can add another bromine. Well, I can add it on any of the places. You can do it step by step, and you can remove all the hydrogen. So if I put a bromine there, what would this thing be called? 1,2-di bromoethane. Okay? If I put another bromine there, what would its name be? 1,2-tri bromoethane. Can you follow that? Okay, they won't go into big detail with it, but if you can follow the trend, it's okay. Do you understand? Because on carbon 1, I have 2 bromines, okay, and on carbon 2, I have 1 bromine, okay. So we list them from the lowest possible numbers. All right. Okay, so this thing is called a haloalkane. And haloalkanes are a fairly useful group of compounds. So when I do a substitution reaction, let's just rewrite it. Hydrogen, hydrogen with bromine, we will get bromoalkane. It can go on any carbon, all right. It can be controlled, but it's not part of our syllabus to know where it goes, so we just stick it onto the end, plus hydrogen bromide. Yes, they do slightly change, okay. Things a little bit like reactivity, and there is a couple of things that changes with it, all right. But the extent of our syllabus, it becomes very specific with catalysts and temperatures and pressures and so on. We don't go into that. All right, so when we do substitution with halogens, we will do it like that. Remember, don't forget that is also formed a hydrogen bromide. Okay. Now, we can do a substitution reaction with water, and the product that is formed is an alcohol. Now, the alcohols also form a group of organic compounds, and their functional group, how do I recognize an alcohol, is an OH group on the molecule. All right? Now, once again, it can have more than one OH group, and that OH group can really go anywhere on the molecule. For our purposes, we usually just stick them onto the one end. Okay. If I go and have a look at the substitution reaction of an alkane with water to form an alcohol, let's take a different one. Let's take propane. Okay, so methane, ethane, propane. There, and hydrogen for the alkane. There we go. And we must add water. Now I'm going to write the water like this. OH, I want to do it like that. Okay. What is going to happen? Well, we need to break off a hydrogen. I don't think one is going to go. Okay. So let me get a smaller rubber. I'm going to take off that hydrogen. And I am going to get, undo. I'm going to take that one, and it's going to go there. And the hydrogen that I broke off is going to go there. You follow? Okay. So, how will I show the addition of, seriously, the addition of water onto an alkane? Well, just very simply, we take any alkane. We did this one with propane. There. Okay, and we are going to add water, HOH. I'm going to write it like that. And what are we going to get? Well, yeah, I didn't write it as an equation. Okay, so what is going to happen? Let's break off that hydrogen, and we are going to end up with OH, and the original structure that we had, plus what are we going to end up with? There's a bit of hydrogen. All right. The substitution reactions. We have done 2 substitution reactions. The one is with halogen to form a haloalkane. The other is with water to form an alcohol. An alcohol functional group is OH. We'll have a look at the group in a little bit. The next reaction of an alkane is called cracking, catalytic cracking. Now, cracking is just very simply you break the molecule. So when I crack an alkane, I get an alkene and hydrogen. Okay, so take any alkane. just take methane, ethane. And I am going to crack it. And I am going to get count the hydrogens. 6, 4, 5, 6. Okay. This thing with a double bond over here is an alkene. Okay. That's the next group of compounds that we will be looking at. Alkenes. So alkanes can undergo combustion reactions. They can undergo substitution reactions. In other words, I can take something off and I can put something else on. The ones that we most often do is with the halogens and with water. If it's a halogen, I get a haloalkane. If it's water, I get an alcohol. After substitution, we can go and crack an alkane. What does catalytic cracking mean? Well, we break up a large molecule into an alkene and hydrogen, or you can break it up. If you have a very long molecule, it's broken up into an alkene and an alkane. It depends. You just, once again, it can be controlled using specific catalysts, specific temperatures, specific pressures. The syllabus does not go into that. All right. Yeah. Yes. We'll have a look at them in a moment. You do get with more. We just work with the one. Okay, we just keep it simple. All right. I'll come back to this one. It's just the next compound we will have a look at. All right. People, after cracking, we get something called polymerization. Now, polymerization is they simply take one molecule and they make it stick onto another one to form long chain-like molecules. By means of polymerization, there is an infinite number of compounds that we can make. Because every time you add an extra molecule onto it, if we used ethane or ethene, then polythene is made from ethene that has been polymerized. Yes, yes, okay. Catalytic cracking, we've just had a look at that. Breaking up of large molecules can be broken down into smaller molecules, and then something called reforming, we don't go into that at this point, can change the shape of the molecules. Now, who knows what Sasol did? What was their big breakthrough? They used coal, technically. That was to make petrol. How could they do it? What does coal consist of? Carbon. They do. That was the later research. Yes. But how can they do it? How could they do it? They took carbon, which is coal or coke, which is carbon, and they made the one carbon, instead of forming a crystal lattice, stick the one onto the other, and then they added hydrogen to it. Water is probably the source. I don't know what their source of hydrogen was, but added hydrogen to it, and from that they could make petrol. No, the previous history was crude oil is distilled, that different fractions are used. And then I think when they started working with it, they discovered, but we can break up longer molecules because it's desirable to have carbon 5 to carbon 10 in a chain for petrol. That's the greatest demand. And that is how they supplied it. But that is basically where Sasol's research comes in. All right. Now Sasol is also a large company, and they are into plastics and a whole lot of stuff. Okay. All right. So that then is the last three processes: polymerization, catalytic cracking, and reforming. That's basically what Sasol did. Okay. Our next group of compounds then after the alkanes are the alkenes, and the alkenes are unsaturated, which means they have a double bond, or, well, the alkynes have a triple bond, but we don't do alkynes. But we find that there are double bonds between consecutive carbons, which means that each carbon is not bonded onto the maximum amount of hydrogens. We say it is unsaturated. The first alkene in the group, what would it be? Would we get methane? Why not? We need 2 carbons with a double bond. So methane only has 1 carbon. So the first alkene is going to be ethene. Yes. Do you understand? Okay. What would propene look like? Like that? Would it matter if the double bond went there? No, it would still just be propene. How many places has carbon got, bonding places? Count them. Yeah, on that side. No, can't. It's got 4 bonding places. 1, 2, 3, 4. Yeah? This carbon has got 4 bonding places. 1, 2, 3, 4. That carbon's got 4 bonding places. 1, 2, 3, 4. All right, carbon has 4 bonding places. That was a good question. Yes. Like that? It's a mirror image of the first one that I've drawn. It is still just propene. All right, now, structural isomers. Because when we get to butene, there's the one. Yes? If we go to butene, 1, 2, 3, 4. 1, 2, 3. I'll show you now in a moment. Hydrogen, 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 hydrogen. Normally we would have called it butene. But butene can look like this as well. Let me do it in a different color. Four, 1, 2, 3, 4, 1, 2, 3, there. These 2 compounds, the red one and the green one, would have the same formula. It would be C1234H8. Okay? But they are not identical. In the one, the double bond lies on the end, and the other one, the double bond lies in the middle. So we need to be able to name them in such a way that we can distinguish between them. The easiest way to do that is to number the carbon where the double bond is, so that the double bond gets the lowest possible number. So it would be between carbon 1 and 2, and on this one, 1, 2, 3, 4, or 1, 2, 3. So it's still between carbon 2 and 3. So the red one, we will call but1 in, because the double bond lies by carbon 1. This one would become but2 in, because the double bond lies between carbon 2 and carbon 3. Would we get but3 in? No, because but3 in would be a mirror image of that one. Okay, if you flip it over. All right. Are you with me? All right. Now, because of the fact that our alkenes are unsaturated, we said the alkenes, oh goodness me, where am I? They form a homologous series, same general formula, CnH2n, and they are more reactive than the alkanes. The reason for that is, when we have a double bond, the second bond is easier to break than that first bond. So if I have single bonds between carbons, they're fairly strong. But if I have a carbon with a single and onto it comes a double bond, then that second bond is easier to break than a single bond. And this makes that the alkenes are more reactive. They are more willing to react than the alkanes. Okay? They will react slightly faster and slightly easier, where, for example, the alkanes, I would have to heat them, expose them to sunlight, add a catalyst. The alkenes would just go naturally. Yes? Yes, because of you need to break 3